Welcome to LIB Academy, and in this video I'm going to take you through beta functions. We're done with gamma functions, now looking at beta functions. And these functions are very important because they help us evaluate integral problems and integral problems with ease, some of them, not all of them. So to continue, we need to know some properties or formulas that we'll be using. The general beta function formula is of the form beta is represented by b, beta of mn equal integral from 0 to 1 x to the power m minus 1 minus x to the power n minus 1 dx, where our m and n here are greater than 0. So this is the general beta function formula. So there are other formulas that we need to know, the relation between gamma and beta. So let's say if we have beta mn equal to gamma m gamma n all on gamma m plus n. So this is the relation between gamma and beta. And another formula we need to know is the trig properties. So when we have to solve problems under trig functions, there is a formula that we can use to do so. So it's half beta of m n equal integral of 0 to pi over 2. Notice the limit very well. Sine 2m minus 1 theta cos 2n minus 1 theta d theta. So for gamma function, the limit is from 0 to infinity. For beta function, the limit is generally from 0 to 1. And this formula is a relation between gamma and beta. And this formula, we are using this to solve trig problems. So notice it very well. And the limit is from 0 to pi over 2. Another formula we need to know is the Euler's reflection formula, which states that beta of n 1 minus n should be equal to pi over sine n pi. And the symmetry properties, which basically states that, which basically is beta of mn is the same as beta of nm. It means when you find a beta of mn, it should be the same as beta of nm. So, and there's another constant you need to know. Beta of 2, 1 is equal to half. That is just by the way. So let's start solving problems. So evaluate beta for 2. To do this, problems of this, we have to use the relation between beta and gamma formula. So if we have beta of mn, it should be equal to gamma m gamma n all on gamma m plus n. So this beta for 2 here is going to give us gamma 4, which way you do it, you are going to get the same answer due to the symmetry property. So gamma 2 right here, 4 right here, all on gamma m plus n, all on gamma 4 plus 2, 4 plus 2, right? So this will give us gamma 4, gamma 2, all on gamma 4 plus 2 is gamma 6. This is 2. Okay. From gamma functions, we know that we have two formulas. Like we have these two formulas that we can also use to simplify this. Gamma n plus 1 equal n gamma n, and gamma n plus 1 equal n factorial. So this formula right here, we'll use this one for fractions, and this formula we use this for just an expression in this form. In this form. So what we want to do is that, and notice that if you have to look for gamma 4, you have to express 4 in a way like in this form. So 3 plus 1, which is 4, is the same as gamma 4. You can't just use it straightforward like this, but you have to break it down into 1 plus something, giving us 1 plus 3 giving you 4. So if it were to be 5, gamma 5, you have to make it 4 plus 1, gamma 4 plus 1. And with this one, nothing changes, because 4 plus 1 is the same as 5. So gamma 4 plus 1 is the same as gamma 5. So if you are able to do it this way, then you can just go ahead and compare your values to this and say that your n is 5. So in this case, gamma 3 plus 1, comparing this to this, my n is 3. So it's just going to be 3 factorial, right? So, and this one is gamma 4. So with this, let's go ahead and simplify the expression here. So we have gamma 4, and gamma 4 we can break it down as gamma 3 plus 1, right? And we can also break gamma 2 down as gamma 1 plus 1, right? All on, we can break gamma 6 down as gamma 5 plus 1. So we know that if we have in this form, then we can go ahead and compare it to the general formula, just n factorial. Comparing this formula to this, our n is just 3. So this is going to be 3 factorial, 1 factorial on 5 factorial. And 3 factorial is just 3 by 2 by 1. And 1 factorial is just 1. And 5 factorial is just 5 by 4 by 3 by 2 by 1. You could see that you can just ignore one of these one. And 1, 2, 3, 1, 2, 3, you can just cancel these ones here. So this is just going to be 1 over 5 by 4, which is same as 1 on 20. So that is the value for gamma beta 4, 2. Well, now that we have this, evaluate beta 3 on 4, 1 on 4. With this problem, we can decide to use the relation between gamma and beta, which is beta mn equal gamma n all over gamma m plus n, right? This one holds. There's also another formula we can use, which is Euler's reflection formula. But before we do that, let's try substituting values in and see. 1 on 4 equal gamma 3 on 4. This is gamma 1 on 4, all on gamma 3 on 4 plus 1 on 4. So at the end of the day, we are going to get gamma 3 on 4, gamma 1 on 4, all on 3 on 4 plus 1 on 4 is 1. So gamma 1 is the same as 1. Okay. So we are left with gamma 3 on 4, gamma 1 on 4, right? They are multiplying. So we have to simplify this. And let me take you back to gamma functions. If we have gamma 3 on 2, we want to simplify this gamma problem. We are going to use the formula gamma n plus 1 equal n gamma n. Since it is fraction, if it were like it, if it is not a fraction, we can use gamma n plus 1 equal n factorial. In this case, we want to represent this term here, 3 on 2 here, in the form something plus 1. and that something plus 1 should give us 3 on 2. So the best way we can do this is just say that we want something that will add 1 to give us 3 on 2. So we can just form an equation and solve for n. So we have n plus 1. We don't know n, should give us 3 on 2. So simplifying this equation, we can decide to multiply 2 by 2. So multiplying 2 by 2. So multiplying 2 by 2. So 2 by n is giving us 2n. 2 by 1 is giving us plus 2 equal this one. When we multiply it by 2, 2 just cancel, giving us 3. So these two cross the equation sign. So it will be 3 minus 2, giving us 2n. So 2n equal 1. So dividing 2 by 2. So our n is just half. So now that we know that our expression here is half plus 1. So gamma half plus 1 is the same as gamma 3 on 2 here. So gamma 3 on 2 is the same as gamma half plus 1. So now that we are able to manipulate this one and into this form, we can just go ahead and say that our gamma n plus 1 is equal to n gamma n. And comparing this to this term, our n here is half, right? So this is just going to give us half n, gamma half. And gamma half is a constant, which is square root of pi. So this is going to give us half square root of pi, which is the same as square root of pi on 2. I hope this one is clear, how I present my work. Yeah. So we are going to employ the same idea here. Let me rewrite this work here. So we solve up to a point, up to this point. So we are getting two gamma functions and they are multiplying. And if we see any two gamma functions multiplying like this, try recalling Euler's reflection formula. And Euler's reflection formula is nothing but that if we have gamma n, comma 1 minus n, it should give us pi over sine n pi. So I want you to know where to apply your formula. So if you see any expression in this from two gamma functions multiplying like this, try applying Euler's formula. And before you apply Euler's formula, you have to do something to your term. So you need this place to be n, and 1 minus n. You need this place to be n, and this place to be 1 minus n. So you can just go ahead and either you take this or this and equate it to any of these. Like any of these. Like, I mean, just take 1 minus n and equate it to any of these values. So you look for your n. So I would like taking this. So 1 minus n should be equal to 3 on 4. So simplifying this, multiplying 2 by 4. So 4 by 1 should give me 4 minus 4 by n. 4n should give me 3 here. If I multiply this plus by 4, this will just cancel, giving me 3 here. So minus 4n equal 3. Let my 4 cross. So it will become negative 4. So at the end of the day, I'm going to get minus 4n equal minus 1 here. So dividing 2 by minus 4, my n should be equal to positive 1 on 4. So it means that, you see, I equated 1 minus n to 3 on 4. So now that I got my value to be 1 on 4, you can see that even this term is 1 on 4. So just leave that term. This is going to be like, let's say, my 3 on 4 right here, gamma 1 on 4 right here is the same as gamma 1 minus 1 on 4, gamma 1 on 4. So comparing this to Euler's formula, you can see that you have your n here. This Euler's formula, you can see that you have your n, let's say your n 1 on 4, and your 1 minus n, 1 minus 1 on 4. So these terms are the same, 1 on 4, 1 on 4. So that's why you are basically looking out for. Immediately you are able to do this, Immediately you are done with this, so you can just go ahead and use Euler's formula. So this is the problem, right? So you can just go ahead and use Euler's formula. So let's say n1 minus n to give you pi on sine n pi. This is n pi. So now you know your n. Comparing this to this, you know your n to be 1 on 4. So this is more like 1 on 4 1 minus 1 on 4 gamma. So equal to pi all on sine n. Your n is 4, 1 on 4, right? So 1 on 4 pi. So pi is just like 180. So we have 1 on 4 multiplied by 180. And this is going to give us 45. So it means here should be sine 45. So we are going to get pi on sine 45. And what is the value for sine 45? So sine 45 giving us root 2 on 2. So this is going to give us pi on root 2 on 2. So which is the same as pi multiplied by 2 on root 2, right? So this is going to give us 2 pi on root 2. So this will be our final answer for this. So that's it for this video, and see you in my next video. We'll continue with beta functions.